Oh hey guys, how are you? Today we're going to be doing some low-speed aerodynamics, including 2D and 3D theory. It's going to be great.
So today we're going to talk about some of the fundamental equations for 2D theory. So we start off with this first one, which is a fairly simple coefficient of lift equation. All three of these equations have been modified so that they're per unit span, which is a much easier way of kind of showing it for two-dimensional theory, so that when you apply it to three-dimensional, you can just multiply it by your wingspan of choice. Okay, and here we've got the lift equation, which is governed by the Kutta-Joukowski theorem, which essentially states that the lift per unit span is directly proportional to the circulation, which is this value k here. Okay, so here we have the general equation for thin aerofoil theory. This can be derived by making certain assumptions about the aerofoil and certain parameters, and then also considering the aerofoil as a single thin camber line. The following equations here can be derived from this, and they simply state that and these are more specific to thin symmetrical aerofoils. So in other words, where the gradient of the aerofoil all the way along the aerofoil is 0. The values in this equation are u is the free stream velocity, dy by dx is the gradient of that individual point along the camber line, alpha is the overall angle of attack of the aerofoil, and then in this portion of the equation, small k is the elementary circulation generated by that individual point along the aerofoil. x1 is the distance to the aerodynamic centre along the aerofoil from the leading edge, and x is the distance to that point of where the elementary circulation is being generated. This general equation for the thin aerofoil theory can be rearranged into this second form here, which is a more general form for the thin symmetrical aerofoil. So essentially the gradient along the entire aerofoil is 0, a nice flat camber line. This rearranges to this, so the integral here has been changed into d theta form as opposed to dx. It's just a slightly easier way of computing the overall calculation. This can then be rearranged to give us this equation here, which gives us an equation for all of the small elementary circulation points, which can then be put into a larger equation for this, which gives us the general circulation around the aerofoil. This general circulation can then be put back into our original Kutta-Joukowski theorem equation here, which will give us the total lift generated by that aerofoil per unit span. The coefficient of lift can also be calculated by substituting it into one of our other two-dimensional lift equations. This gives us that two-dimensional coefficient of lift is given by 2 pi alpha. So in other words, the two-dimensional lift curve slope is 2 pi, is the gradient of that slope. So here we've got a summary of the more important theoretical results and also a little bit more useful information. So the lift coefficient, C little l that is, to tell you that it's per unit span, is given by 2 pi alpha. The lift slope, so dCl d alpha, equals 2 pi. That's the gradient of the lift curve slope for a symmetrical aerofoil or a flat plate. And the quarter chord location, so that's what the small c represents as the chord. C over 4 is both the aerodynamic centre and the centre of pressure of our aerofoil that we're analysing. We can then use Fourier series to express general thin aerofoils, where the mean camber line is expressed as a function of x or theta. In other words, where the value of dy dx isn't 0, so we've got non-symmetrical aerofoils, we can use this to simplify our equations and make them a little more manageable. And now we've got a few useful expressions that have been derived from this section of the notes. So first of all, we've got the lift coefficient per unit span, which is given by 2 pi alpha, which is the angle of attack times by the lift curve slope, and this is added on to pi times by a1 minus 2a0. Both of these are parameters calculated from the Fourier series above here. This section adds on a small angle, which is the difference between the actual 0 lift angle of the aerofoil up to the point at which the aerofoil is actually set on the side of the aircraft. This next equation is the 0 lift, so essentially it's a rearranged version of this, which can be assumed at the point where lift is 0, therefore CL is 0. So you take CL out of the equation and move this section of the equation over to the opposite side. This is useful if you either need to calculate the angle of attack at which 0 lift is gathered, or if you need help calculating or checking your Fourier series parameters. The 0 lift incidence is, again, like I said, a rearranged version of this, so divide the 2 pi across and it will give you this bit here. All of these equations can essentially be compressed into one down here at the bottom, which is the coefficient of lift is equal to 2 pi times by alpha, which is the overall angle of attack of the airfoil, minus the 0 lift incidence. Now we're going to talk about some of the differences and similarities between two-dimensional theory and this three-dimensional theory. The key point being that they are both inviscid theories, so we're not considering any viscous effects from the air. One of the main things is that we are considering the span in these equations, where our equations before were per unit span. This time we can include those. We're also considering the wingtip vortices, which is generated by having a lift distribution across the wing, which we're also going to talk about the span-wise lift distribution. We've then also got the wing considered as a vortex lifting line. So this is a bound vortex bound to the aerodynamic centre of the wing, which is also described in Prandtl's lifting line theory. So first of all, the vortex system. We've got Helmholtz's vortex theorem here, which states that the strength of the vortex filament must be constant all the way along all of these four sides of the vortex. And all four of these sides of the vortex are required to bind the vortex together, because the vortex cannot end in the fluid. It has to either extend to infinity in that fluid, or it has to end at a boundary between the fluid and some solid surface. So this requirement can be satisfied by having the starting vortex here, which follows the trailing edge of the wing, these being the tip vortices, and here having the starting vortex, which of course is going to create an overall downward motion in the centre of all of these as they're all twisting inward, and this is known as downwash. Now here we've got the lift distribution across the span of a wing. Now the lift at the tip of the wing has to be 0, which shows this ideal lift distribution that you'll get across the wing. You want the most lift to be generated at the centre of the wing. This also helps avoid tip stalling in aircraft, which is very worrying because it means that you no longer have any roll control of the aircraft if the tips stall, but you've still got the roots generating lift. Here we've got an important list of the theoretical equations that we've generated from this three-dimensional theory. So first of all, we've got this lift equation here, with the terms being air density, free stream velocity, circulation around the wing being a constant in Helmholtz's lifting line theory, pi constant obviously, b is then wingspan of the aircraft. We then also have the lift coefficient, which is a rearranged form of this equation, and then we also have the circulation equation, which again is another rearranged and slightly substituted version from our obvious lift equation, where lift equals a half rho v squared s cl. We've then got an equation here for the downwash, which is the vertical velocity of the air following the trailing edge of the main plane. This K0 here is the circulation generated by that wing, and B is the span of the wing. So the bigger the span, funnily enough, the smaller the downwash's velocity is going to be. We've then got the induced angle. This is the angle which is essentially the angle of attack is reduced by due to induced drag being generated. And this is equal to the coefficient of lift of the wing divided by pi times the aspect ratio, which is a function of the span of the wing and the chord depth. Then we've got induced drag here, which shows how the induced drag is equal to the induced angle we've just calculated here and the overall lift generated by the aircraft. Drag coefficient can then be calculated, which is the same as here. You just substitute the coefficient of lift in for the lift and the coefficient of drag in for the drag, which is also equal to the coefficient of lift squared divided by pi times by the aspect ratio again.
Alright, thanks for watching, guys. I hope this video was useful. If you've got any questions and stuff, leave them down in the comments. If you enjoyed the video and found it useful, please leave a like, subscribe and anything, and we'll see you guys next time. Thanks for watching.